In this video tutorial, we will introduce the concept of rates of reactions. The rate of a chemical reaction describes how quickly reactants are being converted into products. So in general, we can express this using the equation reaction rate is equal to change in quantity per a set amount of time. So we can measure how quickly the product concentration is increasing per unit time, or how quickly the reactant concentration is decreasing per unit time. So how quickly are we making a product, or how quickly are we using up the reactants? If we measure the change in product concentration or reactant concentration per unit time over a given time interval, so for instance from 10-second to 40-second mark, this gives us the average rate of reaction over this time interval. On the other hand, if we want to measure the change in product concentration or reactant concentration per unit time at a specific point, then that is called the instantaneous rate of reaction. So the slope of the secant provides us with the average rate of reaction over that given time interval, whereas the slope of the tangent provides us with that instantaneous rate of reaction at that specific time point. Alright, so let's do a sample question. Nitrogen dioxide is being produced at a rate of 5 times 10 to the power negative 6 moles per liter second. But what does mole per liter second mean? Well, if you recall, slope is equal to rise over run. In this case, rise is the concentration measured in moles per liter, while run is the time measured in seconds. We can then write that as moles per liter divided by seconds, or if you want, seconds over 1. And when we try to divide fractions, we multiply by the reciprocal, so it becomes moles per liter times 1 over second, which gives us moles per liter second, or if I want to write it all in one line, mole times liter to the power negative 1, seconds to the power negative 1. So, given that information and the equation below, what is the rate of decomposition for N2O5, and what is the rate of formation for oxygen? Now, you don't have to organize your information this way. I did, because it just graphically makes sense to me this way. You'll notice that the value was 5 times 10 to the power negative 6 of nitrogen dioxide. That's the value that was given to us over here. And then it's a 2 to 4 ratio of N2O5 to NO2. So for every 2 N2O5s, 4 NO2s are produced. So that's why it's a 2 over 4 ratio. Same thing with the oxygen. It is a 1 to 4 ratio. So for every 4 nitrogen dioxides, there's going to be 1 oxygen. So that's where I got the 1/4 from. So using these stoichiometric ratios, I can determine the rate of N2O5 consumption and the rate of oxygen production in this case. All right, so half as much over here and 1/4 as much over here. Now, there are several ways to experimentally determine the rate of chemical reaction. The nature of the chemical reaction typically determines the technique that we are going to use. So for instance, if no gas is produced in my chemical reaction, I probably would not measure volume or pressure. Or if the reaction doesn't change color, then you probably wouldn't want to use a spectrophotometer. So it is important that you choose the right property to be measured for the particular chemical reaction.
The volume of a gas is proportional to its molar amount. Measuring the volume of a gas evolved in a chemical reaction provides a means of monitoring the course of the reaction. When one of the reaction products is a gas that escapes from the reaction mixture, the reaction rate can be studied by weighing the reaction mixture and observing how its mass changes with time. For example, the rate of glucose fermentation can be studied by this method, since a reaction product is gaseous carbon dioxide. Since the amount of gas N is related to its pressure P by the equation PV equals nRT, measuring the pressure of gas evolved in the reaction at constant volume V and constant temperature T allows determination of the reaction rate. When the reactants and products differ in color, the reaction can be monitored by observing the changes in color intensity using a colorimeter. This method can be employed to study the reaction of bromide ions with bromate ions. Bromide and bromate ions are colorless, but their reaction product, bromine, is red-brown. Observing the color changes allows the progress of this reaction to be monitored. Conductance is the ability of a solution to carry electric current. It can be measured with a conductometer by inserting 2 electrodes into the solution, applying a voltage, and recording the current passing between them. The hydrolysis of methyl methanoate can be studied by this method, since the conductance of sodium ethanoate, the reaction product, is much lower than that of sodium hydroxide, the reactant.
So these are just some of the properties we can measure in order to track the progress of a chemical reaction. As a reminder, you are not limited to measuring what is being produced, you can also measure what is being used up. Now, if you recall, collision theory states that chemical reactions occur when reacting particles, such as atoms or molecules, collide together. However, not all collisions will successfully create a new product. In order to be successful, a collision must fulfill two criteria. First, the collision geometry, or the orientation of impact, must be favorable, so they must collide with the right angle.
Consider the reaction of two AB molecules to give products A2 and B2. The reaction takes place only when the molecules are oriented in such a way that atom A is able to react with atom A and atom B with atom B. When A meets B and B meets A, the reaction yields unchanged reactants and no net reaction takes place. Any other orientation will result in the molecules ineffectively bouncing off one another. The collision is effective only when the mutual orientation of the molecule allows the reaction to occur. Note that you can find only one correct effective orientation and thousands of others which are ineffective. This means that the probability of the correct orientation occurring is quite low. For this reason, most collisions are ineffective. That explains why many reactions are so slow. Still, it is amazing that some reactions are so fast.
Secondly, they must collide with sufficient energy, so we call that activation energy, or EA, the energy required to start up the chemical reaction.
Consider a very simple reaction of A and B to give the product AB. The molecules of A and B must collide for the reaction to take place. The collision of two molecules is different from the collision of two billiard balls. Molecules are not hard, elastic objects with definite, sharp outer boundaries. Instead, the electron cloud of a molecule is rather soft and fuzzy. When two molecules approach each other, their electron clouds come into contact and mutually repel one another because of their negative charge. The closer they come to each other, the stronger the repulsion. When the electron clouds of molecules penetrate each other to such an extent that a reshuffling of electrons becomes possible, the reaction occurs and a new bond forms. Slow-moving molecules possess insufficient kinetic energy to overcome the repulsion between electron clouds. The collisions of such molecules are ineffective. Only when the combined kinetic energy of colliding molecules overcomes the intermolecular repulsion can the collision be effective and chemical reaction take place. This minimum energy required for the reaction to occur is called the activation energy.
So by improving these two criteria, we can increase the number of successful collisions, thereby increasing the reaction rate. Now, during a successful collision, old chemical bonds must be broken, while at the same time, new ones are going to be formed. That split second where all the old bonds and new bonds exist all at the same time is called an activated complex. This is the most energetically unfavorable, or the most unstable point of the collision. So unless the particles collide with the correct orientation and energy, the activated complex cannot form properly. As such, the collision is ineffective and no products are formed.
Let's consider the reaction occurring between two AB molecules, forming products A2 and B2. For the reaction to occur, two molecules of AB must collide. As they approach each other, mutual repulsion causes them to slow down. The kinetic energy associated with their motion decreases and is converted into potential energy, which builds up until a maximum is reached when the activated complex is formed. Up until this moment, energy is consumed. The difference between the potential energy of the reactants AB and the potential energy of the activated complex A2B2 is equal to the activation energy for this reaction. The activation complex is a highly unstable combination of atoms and quickly breaks up into products. Energy is released and is transmitted into kinetic energy associated with the motion of the product molecules. The shape of the curve in the potential energy diagram indicates that in every reaction there is a kind of energy barrier that must be surmounted for the reaction to be able to proceed. The height of this barrier represents the activation energy. The energy difference between reactants and products equals the net energetic effect of the reaction. In our case, the energy is released in the form of heat, since the energy of the products is lower than the energy of the reactants. The reaction is exothermic. Note that for the reverse reaction, where A2 and B2 form two AB molecules, the activation energy is higher. The existence of the energy barrier explains why some reactions are slow and some are fast. Reaction rates depend on the magnitude of the activation energy. The higher the energy barrier, the slower the reaction.
So, as we saw in that video, a potential energy diagram describes the progress of a chemical reaction. If the potential energy of the reactants is higher than the products, then it's going to be an exothermic reaction as it releases energy, so that delta H will be a negative value. If the reactant energy, potential energy, is lower than the products, then that means it's going to be an endothermic. It must absorb energy to reach the final product stage, so that would be a positive enthalpy value. The difference between the energy, or rather the potential energy of the reactants to the activated complex is known as the activation energy, the energy required to start the reaction up. In an exothermic reaction, the EA values are generally smaller, versus an endothermic reaction, the EA values are going to be much larger. Because endothermic means to absorb energy, while exothermic means overall you're releasing energy. Please keep in mind that you will have to specify if it's EA forward, so activation energy in the forward direction, or EA reverse, so that'd be energy required to go in the reverse direction instead. Alright, so activation energy is the minimum amount of energy required to initiate a chemical reaction. It is independent of delta H, so delta H and EA are not related to each other. As we'll see later in this lesson, I can have a very large activation energy and then reduce it using something like a catalyst into a smaller activation energy, and yet for both scenarios, I would still have the exact same enthalpy value. So activation energy is the reason why highly flammable substances do not spontaneously combust. They do require that initial spark to activate or initiate the reaction. Alright, so initial spark right there. But once the activation energy barrier has been overcome, the heat of the reaction, the change in enthalpy, because it's typically an exothermic reaction if you're going to burn something, provides enough energy to overcome the activation energy for the remaining molecules. And that's why when you burn gasoline, you don't have to keep sparking it. The initial spark produces enough energy to allow the remaining gasoline molecules to overcome their EA and then, of course, continue on with the exothermic combustion reaction. Just keep in mind that when you are doing the reverse reactions, enthalpy values must change signs. So going in the forward direction, this reaction is exothermic. It is going to release energy. That's why its enthalpy value is a negative value, going from a high potential energy reactant to a low potential energy product. On the other hand, if you're going in reverse, the enthalpy magnitude is going to be the same, but it should be a positive at that point, because when you're going in reverse, you're adding energy to go from low to high and adding energy to get there. Now in this diagram, they call it a transition state, but we will refer to it as an activated complex. In any case, the heat of the reaction, the overall enthalpy for the reaction, is equal to the forward activation energy minus the reverse activation energy. So once again, only successful or effective collisions will result in the formation of products. And if the number of successful collisions increase, then more reactants are being converted to products, and as such, the rate of reaction has also increased. In general, there are 5 factors that can affect the rate of reaction. The first is reactant concentration. If you have more particles present, they are more likely to collide. Alright, the more crowded things are, the more likely they are to run into each other. However, this does not improve the likelihood of a successful collision. Instead, it improves the overall number of successful collisions. So let's say I have a 1% chance of colliding successfully. Well, 1% of 100 collisions is only 1. But 1% of 1,000 collisions is 10. So in this case, I haven't increased my chances of a successful collision, but I have increased the number of successful collisions per second by having more collisions. It's like buying more lottery tickets. Each individual lottery ticket is not more likely to win, but by buying more lottery tickets, I've improved my overall chances of winning. Anyway, the reverse is true for lowered concentrations. So the fewer collisions you have, then of course the fewer number of successful collisions per second you will have as well, thus reducing the rate of reaction. Another variable that affects the rate of reaction is temperature. Temperature is defined as the average kinetic energy of a system. So the higher the temperature, the faster those particles will move. In so doing, this increases the number of collisions. It also increases the number of molecules with the minimum activation energy required to achieve that successful collision. And vice versa, lowering the temperature decreases the number of overall collisions, but also decreases the number of molecules that have that minimum activation energy, thereby reducing the rate of reaction. For gases, we can also play around with pressure. Pressure can be increased by decreasing the volume or introducing more gas particles. Again, this will increase the concentration and thereby allowing particles to collide more often. And of course, the reverse is true for lowered pressures. The next variable that can affect rate of reaction is typically used for solids, and that is surface area. By increasing the surface area, so for instance going from a solid to a powder, it exposes more reactants to collisions. This in turn increases the number of successful collisions per second. Finally, the use of a catalyst has an effect upon the rate of a reaction. Typically, catalysts work by lowering the activation energy and providing an alternate reaction pathway where a new, lower energy activated complex can be formed. So without a catalyst, you need this much activation energy to overcome the activated complex. But with a catalyst, we are provided with an alternate reaction pathway, one with a much lower activation energy. So it's like using a ramp versus a staircase. In both scenarios, you start off at the same place and you end off at the same destination. But the ramp is significantly more accessible than a staircase. More people can make it up a ramp than on the stairs. So by lowering the activation energy threshold, more molecules now have the minimum energy required for a successful collision, which means more products will be formed. Now please take note, catalysts are not consumed in a chemical reaction, and biological catalysts are called enzymes.
Consider the potential energy diagram for the exothermic reaction. Reactants give products. If the reaction is to occur, the reactants need to possess a joint energy exceeding the activation energy. As we can see from the Maxwell-Boltzmann distribution curve, only a few reactant molecules have sufficient energy. The reaction will be very slow. What happens when the reaction is carried out in the presence of a catalyst? Catalysts lower the activation energy for the reaction. Now many more molecules have an energy level exceeding the new, lower value of the activation energy. The number of effective collisions increases, and the reaction rate rises. Catalysts reduce the activation energy by providing an alternative route for the reaction. In other words, an alternative reaction mechanism. For example, the hydrolysis of esters, like methyl ethanoate, is relatively slow when the ester reacts with water. The reaction requires the lone pair of the oxygen atom in the water molecule to approach the carbonyl carbon atom. There is only a weak partial positive electrical charge on this carbon atom. Therefore, the attraction of the water molecule to the reaction site is not very strong, and so the reaction has a high activation energy. Ester hydrolysis can be catalyzed by acids, though. A positively charged hydrogen ion bonds to the oxygen carbonyl atom. A carbocation is formed, with one positive electrical charge situated on the carbonyl carbon atom. A water molecule is attracted to this reaction site much more strongly. The reaction has a lower activation energy and can proceed much more quickly. Addition of acid alters the reaction mechanism. The single-step reaction with a high activation energy is replaced by a two-step reaction with a much lower activation energy. Notice that the hydrogen ion is recovered at the end of the reaction. As the catalyst, it is not chemically changed in the course of the reaction.
Now, the rate law is a tool we can use to determine how much of an effect a particular reactant has on the overall rate of reaction. If you recall, the rate of reaction is proportional to the concentration of the reactant. So if you have a high concentration of a reactant, then chances are you'll increase the reaction rate, and vice versa. Decrease the reactant concentration, you decrease the rate of reaction. As such, a rate equation can be written to quantifiably relate the concentration of the reactant and the reaction rate. So for this generic equation with reactants A, B, and C, where the lowercase letters represent the stoichiometric ratios. We can determine those by balancing the equations. You can create an equation, a rate law equation, where rate is equal to K, concentration of A to the power of X, concentration of B to the power of Y, and concentration of C to the power of Z. Rate is measured in moles per liter second. K is the rate constant for a given reaction. If this K value is very, very large, when you multiply it, you get a very high rate of reaction. If the K value is small, then when you multiply by a small number, of course, you get a very small rate of reaction. A, B, and C are the reactant concentrations measured in moles per liter. And finally, the exponents X, Y, and Z are the reaction orders. So we say X is the reaction order with respect to reactant A. Y is the reaction order with respect to reactant B, etc., etc. Now, unlike in the equilibrium units where the exponents were the coefficients, this is not the case with the rate law. X, Y, and Z, these exponents must be experimentally derived. So let's go over a sample question in order to better understand how this works. So given the following data for this specific reaction, we want to come up with a rate law expression. To determine the exponent for reactant A, I'm going to compare trials 1 and trials 2. By doubling the concentration of A, you'll notice that I've also doubled the rate of reaction. Now, how do I know that B had no effect on this rate change? That's because I kept the concentration of B constant. I didn't change it. The only changes that were made were from the concentration of A. And so I know that any changes that occurred over here were due only to the changes in A and had nothing to do with B. So that's what I mean when I say that these exponents are experimentally derived values. You have to purposely design the experiment trials so that only one variable changes at a time and all the other ones must remain constant. Otherwise, if you change two items at the same time, then this change over here, this change in rate of reaction, is due to which one? How do you know which reactant had what kind of an effect? So we have to keep all the reactants consistent and only change one value at a time. Alright, so I doubled the concentration of A, and that's represented here by the number 2. And the effect is that I've doubled the concentration, or the rate of the reaction. And that's this number 2 over here. So the rate order is the exponent. 2 to the power of what equals 2? Well, the answer is 1. And that's why A is a first order reactant, or we say the order of reaction with respect to A is 1. So its exponent is a 1. Now, if I wanted to find out what the exponent is for B, I would have to compare trials 2 and 3. In so doing, I've kept the concentration of A constant, so that has no effect, but I've doubled the concentration of B. So by doubling the concentration of B, that's the number 2 over here, I've had an 8-fold effect. All right, the rate of reaction is octupled, so now that's an 8. That's where it's represented over here. So 2 to the exponent of what equals 8? The answer is 3. So therefore, the order of reaction with respect to B is 3, or you can say that B is a third order reactant. Now, for the purpose of this course, these exponents will always be nice whole numbers, so your calculations will not be difficult. You won't encounter any fractions of an exponent. All right, they'll always be nice, whole, pretty numbers for this course anyway. So there you have it. A is a first order reactant with an exponent of 1. B is a third order reactant with an exponent of 3. So now that I have this information, I know which reactant I'm going to invest more money in. So for instance, if I want to speed up the reaction, I'm not going to waste my time trying to increase the concentration of A because it only gives me a double return on the rate of reaction. Instead, I'm going to spend my money by increasing the concentration of B and keeping the concentration of B very high in order to octuple my rate of reaction. And that's one of the many uses for the rate law. The rate law expression tells us which of these two reactants has the greater overall effect on the rate of reaction. Now, if a question ever asks what is the overall order of reaction, just add up all the exponents. Right? So if you have a very high overall order of reaction, that means playing around with concentration will have a huge effect on your rate of reaction. If your overall order of reaction is a very low number, that means changing the concentration won't have much of an effect. You probably want to play around with a different variable instead. So maybe spend your time and resources on increasing temperature or the catalyst instead of concentration. Now, we're not done yet. We still need to solve for the K value. To determine the value of K, substitute the values from any trial into the initial rate expression. So in this example, here's our rate expression. I'm going to substitute the values from trial 1. You don't have to pick trial 1. You could have done 2 or 3. Just make sure you choose only the values from that specific trial. Once I plug in the values, so 0.5 into the rate, 2 for the concentration of A, 1 for the concentration of B, solve algebraically, and you get a K value of 0.25 moles to the power negative 3 liters cubed seconds to the power negative 1. I would also accept 0.25 liter cubed per mole cubed second. Now on my test, typically you get 1 mark for the actual value and 1 mark for the proper units. So make sure you brush up on your algebraic skills. Alright, so try out the sample question yourself. Press pause. When you're ready, press play, and we will take it up together. Alright, so I probably would have compared trials 1 and 2 in order to determine the order of reaction for reactant B, because with 1 and 2, reactant B changes, but reactant A does not. To determine the order of reaction for reactant A, I would probably compare trials 1 and 3. By looking at 1 and 3, the A concentration changes, but the B concentration remains constant. So with B, the concentration of A doesn't change, but the concentration of B does change. It triples, so that's where the 3 comes from. So when I take 4.5 times 10 to the power negative 2 and divide it by 5 10 to the power negative 3, I find that there's a 9 times increase in the rate of reaction. And that's where this value comes from. So 3 to the power of what equals 9? The answer is 2. So therefore B is a second order reactant. With A, I'm comparing trials 1 and 3. The B concentration doesn't change, but the A concentration is doubled. All right, so because it doubles over here, that's where this number comes from. Then I took 5 times 10 to the power negative 3, divided by 2.5 negative 3, and I get the answer is 2. So the rate of reaction is also doubled. So 2 to the power of what equals 2? The answer is 1. So therefore A is a first order reactant. From there, I substitute this into my rate expression. Rate is equal to K times A to the power 1, B to the power 2. And then I'm going to choose any trial I want and substitute those values in and solve for K. And then you'll get 2,500 moles to the power negative 2 liters squared, second to the power negative 1. Or if you want, 2,500 liters squared per mole squared second. The overall rate of the reaction is the exponents added together. So rate order of 1, rate order of 2, add them together and get a 3. And this would be your overall rate law expression. So as we mentioned earlier, reactants with a higher rate order have a greater effect upon reaction rates as they are more sensitive to changes in concentration. Now, be aware, zero order reactants are possible. If you recall, anything to the power of 0 is always equal to 1, so that means the rate remains constant. That tells you that if you have a reactant that's zero order, that particular reactant has zero effect, no effect upon the overall rate of reaction if you try to change its concentration. Our final topic is that of reaction mechanisms. A reaction mechanism is a series of elementary steps that describes the progress of the overall chemical reaction at the molecular level. Most chemical equations you encountered in grade 9, grade 10, grade 11, they were only concerned with the initial reactants and the final products. So what was it at the start? What is it at the end? They did not take into consideration the intermediate chemical species that are formed during the actual reaction. You can think of these elementary steps as their own small chemical reactions, each one with their own activation energy and their own unique enthalpies. In order to really control a chemical reaction, you can't just know what it was and what it is going to be. You have to know the path it took to get there. So we know the activated complex in each of these elementary steps is the most unstable point of the chemical reaction. But you can think of the intermediates as almost a resting stop in between. So elementary step number 1, resting spot. So the products in the first elementary step become the reactants for the next elementary step. Then here's another resting spot, another intermediate. Then these intermediates become the reactants for the next and final elementary step before we get to our final products. So if we look at this example, N2O will decompose eventually into nitrogen gas and oxygen gas. It does this through a two-step process. First, N2O will decompose into nitrogen gas and monatomic oxygen. We know that monatomic oxygen is very, very unstable. And so this intermediate step becomes the reactants for the final elementary step. The N2O will then react with monatomic oxygen to produce N2 and O2 in the end. Because the monatomic oxygen appears on the reactant side once and the product side once, it kind of cancels each other out. It's used up in the subsequent step, so it never appears in the final part. So we can take it out in our overall net equation. Because I require 2 N2Os in order for this reaction to occur, that's why the Balanced equation requires 2 N2Os, and 2 nitrogens are produced during the process at the first elementary step, and then the second one in the second elementary step for a total of 2 nitrogens being produced. So in general, intermediates that are formed in an elementary step are consumed in subsequent elementary steps. Now, the reason why we didn't concern ourselves with the intermediates during grade 10 or grade 11 is because they don't last very long. They last for fractions of a second. In fact, the study of these elementary steps is called femtochemistry, and that is derived from the term femtosecond, which is 1/1,000,000th of a billionth of a second. So how is it possible for you to record the actions of a molecule, the chemical reaction itself, the movement of the atoms, if they last for fractions of a second? Well, this is pretty ingenious. First, you have a molecular beam that fires out the reactants, and you have a starting pulse. All right, so using a laser, the starting pulse of the laser activates the reaction. Then you have a secondary pulse that records the action, but using these mirrors, that secondary laser pulse reaches the beam, the molecular beam, a femtosecond later, or just a few femtoseconds afterwards. So the red beam arrives first, but because they both travel the speed of light, but this one travels a little bit further, it arrives a few femtoseconds after the reaction has been activated. Then it detects what did the molecule look like at that point. Then you again fire out the molecular beam, shoot out your pulse, but then cause this blue laser to come by a few femtoseconds after that. And then you record what it looks like then. And so over a series of shots, you are able to determine what did the molecular structure look like? What did the molecules, the arrangement of molecules look like or appear during the course of the chemical reaction? And from there deduce what those intermediaries look like. Pretty ingenious stuff developed by Ahmed Zewail, who was an Egyptian chemist. He actually won a Nobel Prize for his research into this and developing femtotechnology and the field of femtochemistry. So, using femtochemistry, we are able to get a better picture of how a chemical reaction progresses over time. Now, the elementary step that proceeds the slowest is known as the rate determining step. It limits the overall rate of reaction. Just as the slowest moving vehicle on a single lane road determines the overall flow of traffic, the slowest elementary step determines the overall speed at which the reactants are being converted to products. So in this example, it doesn't matter how quickly I'm able to convert NO into N2O2. So even though this step is also very fast, we don't have the reactants for this reaction to go through because we're always waiting for step 2 to create these guys over here. Normally, the RDS, the rate determining step, is the one with the highest activation energy and or the elementary step with the most number of intermediates involved. Alright, so if you have enough energy to overcome the first activation energy, that's great, but when you come to the second elementary step, if you only have that much energy, you can't make it past this elementary step, and so then you'll fall back down into an unsuccessful collision. But if you have enough activation energy to overcome the second elementary step, so we call this the rate determining step, then if you've got enough energy here, you definitely have enough energy to overcome this one, and you definitely have enough energy to overcome this one. So this one is called the rate determining step. This basically prevents molecules from making it to the final product. As such, it directly impacts how many reactants will successfully collide and turn into products. In this next example, the first elementary step is the rate determining step. It is the slowest step in the overall chemical reaction. So it doesn't matter what the hydroxide concentration is for the second step because it's always going to be waiting for this molecule to be produced from the first step. So it doesn't matter how much hydroxide concentration I have, it will always be waiting in excess to react with the first intermediate, and as such my hydroxide ion is going to be 0 order. And as I mentioned earlier, anything to the power of 0 is always equal to 1. So changing this hydroxide concentration to the power of 0 has no effect. This value will always be the same. So rather than wasting time and resources trying to improve the concentration of hydroxide ions, I should instead try and improve the concentration of this particular ion in order to speed my reaction up. Alright, so in this example over here, using this diagram, we can determine which is the rate determining step. That's probably going to be elementary step number 2 because it has the highest activation energy required. And finally, which would be the overall activation energy for this reaction? That would probably be over here. So the amount of energy required to activate the entire reaction would be this amount, because if you have this much energy, you definitely have enough to overcome this elementary step and this elementary step with their individual activation energies.